Good morning friends. In today's video we are going to see the pipe sizing of chilled water. So here in the roof you can see there are different FCUs are located in GSM room, MEP room, electrical room. Also you can see the AHU and moving further you can see the FAHU and AHU, different AHUs are there. So first the outline of the project here is, so what you see here is the heat exchanger room, like you see in the heat exchanger. We have two heat exchanger here. We can say like a heat exchanger room or ETS, energy transfer room. And here from the heat exchanger the line is serving to different FCUs and AHUs located in the different parts of the floors. There are two pipe sizing methods available for the chilled water pipe sizing. So one is called as a velocity method and second one is a velocity plus friction method. So let me tell you both methods and then I will tell you which method I am using for my design, then you can finalize. So if you see the career handbook for the chilled water pipe sizing, you can see the different velocity range. For example, pump discharge, the velocity should be 8 to 12 feet per second, pump suction line 4 to 7 feet per second, and header line 4 to 15, riser line 3 to 10 feet per second, like that. So let me tell you where they are pointing out this position. For example, if you see here, so this is the riser diagram, what you see here. So I will highlight here also. Okay, so you can see this line. So this is the riser line and the maximum velocity for the riser line as per this line 3 to 10 feet per second you have to follow. And similarly if you go down, you can see this tapping line. The tapping point is here. So this tapping point which is going to this point. So this is the tapping line and also the header line. The header line means near to the pump. So pump's discharge header is there, na, that line. So in the header line they have given the maximum velocity, like you see here. The maximum velocity of the header line is 4 to 15 feet per second and riser line I already we discussed 3 to 10 feet per second, and pump suction and discharge 8 to 12 in the discharge line and 4 to 7 in the suction line. Similarly, pipe sizing, if you go to ASHRAE application handbook, you can see the pipe sizing limit for the general service, city water, boiler feed and pump suction and discharge line, pump suction and drain lines. Here the first method is called as a sizing based on velocity method. In the velocity method, the pipe is sized based on its location. For example, if the pipe is located in the roof or the header area near to the pumps, and the maximum velocity must not exceed 4 to 15 feet per second, and normally we use 10 feet per second. We don't need to go to the maximum limit of 15, so it's safe to use 10 feet per second. And the riser one as I explained in my drawing here. So this pipe is called as a riser pipe, which is coming from which is extending from top to bottom. For the riser line, the velocity is 3 to 10 feet per second. Normally the riser is going into the soft area. So 3 to 10 feet per second is the maximum velocity, and we'll follow maximum 10 feet per second, not exceeding 10 feet per second. And tapping from riser. So if you go down, if you see here the tapping point, as I indicated here, this is the tapping point. So from here it is going to the different room. These are different rooms in the floors it is going. So tapping area 5 to 7 feet per second we can follow, and maximum velocity not to exceed 7 feet per second. And the second important method we call is velocity plus friction method. In this method, the location of the pipe, whether it is in the shaft, whether it is in the header or in the roof, is not an important thing. In this method, we will consider mainly two items. One is the velocity and second is the friction loss. So this is the method mostly I use in my design. So let me explain you that concept. So if you go to this ASHRAE application handbook pipe sizing, so you can see this wording. For example, here recommendation place that velocity limit of 4 feet per second for 2-inch pipe and smaller, and 4 feet of water per 100 feet head loss or pressure drop if the pipe size is more than 2 inch. So till pipe size is 2 inch and smaller, we can see the velocity limit must not exceed 4 feet per second, and if it is above that one, then we need to make sure that the head loss is not exceeding 4 feet per 100 feet. Let me explain this one, then it will be clear for you. For example, this FCU RF02, which is serving for the GSM room, which needs 40 GPM water flow into the FCU for the cooling capacity. So let me open this pipe size, then I will come to how this 40 or 50 GPM, how the value we need to determine. So first, if you see the pipe size, the pipe material will come here. So if you see here the copper pipeline type KLM copper, the PVC pipe, ABS, and there are different schedule for the steel pipe is available. So for the carbon steel means for the chilled water application, normally we are using schedule 40. So I prepared I posted a separate video how to to size the pipe sizing, pipe thickness. If you have not watched that one, please have a look at that one. So settle 40 steel we are using for the chilled water pipe sizing. And if you go to the temperature, you can see 50 degrees, 70 degree, different temperature limit is given. So 50 degree Fahrenheit means normally it will come 10 degrees Celsius. So normally for the chilled water application we are using this one. If you go to 70 degree Fahrenheit, it will be around 25 degrees Celsius, which is not applicable for chilled water. We will normally use the 50 degree Fahrenheit that is equal to 10 degrees Celsius. So here the pipe sizing they have given, it's like a trial and error. For example, I will put any size. For example, I put 1 inch, and here the required flow is 40 GPM. As I mentioned here, I need 40 GPM. So if you put 40 GPM, the first what they are telling, till the pipe size 2 inch. For example, if you see here, if the pipe size is less than 2 inch, the velocity should be lower than 4 feet per second. So if you go here, I put any size first for 1 inch, which is less than 2 inch only, and I put 40 GPM. If you see the velocity limit here, which is 14.85 feet per second, which is here at this point 14.85 feet per second, which is very high, so which is not acceptable. So I will increase the pipe size to 1.5 inch. Now again I will put 40 GPM. The fluid velocity is 6.3 feet per second, so which is again not acceptable. So I will put 2 inch now, and I'll put 40 GPM. If you see the fluid velocity, which is 3.82 feet per second, so which is less than 4 feet per second, so it is acceptable. So the pipe size for this FCU, just for example, if it is 40 GPM, then the pipe size should be 2 inch. That means the chilled water supply pipe and return pipe should be 2 inch. Let's say this FCU it needs 60 GPM. Let's see what is the pipe size will come. For example, here I will put 60 GPM. If you see this velocity 5.74, but here what they mention, first of all the case is it is 5.74, which is exceeding the 4 feet per second velocity. So that time if you go to this one, if the pipe size is less than 2 inch, then 4 feet per second is acceptable. But if it is more than 2 feet per 2 inch, then we don't need to see the velocity. We need to see the head loss only. So that is the important thing here. For example, here if you put 2 inch and if you put 60 GPM, the velocity is more than 4 feet per second. That means the 2 inch pipe is not sufficient to hold this 60 GPM. So the next thing you have to increase the pipe size 2.5 inch, and again I will put 60. And if you see here, the velocity is 4 feet per second. So as I told you, till 2 inch we have to see the velocity. If it is more than 2 inch pipe size, then we don't need to see the velocity. That is why the method is called as a velocity plus friction method. So that time you have to see the head loss only. So for 2.5 inch, that means we exceeded the 2 inch. If you see the head loss, it is 2.773 feet per 100 feet. So our maximum limit is 4 feet per 100 feet. If the pipe size is more than 2 inch. So that means this is acceptable one. If you see here, the fluid velocity, the head loss is 2.773 feet per 100 feet. So the pipe size is 2.5 inch for 60 US GPM. Now we need to know this 40 GPM or 60 GPM, how it comes. So there are some formulas we need to understand the basic. Then we will come to know how this value comes. So here we have a formula. GPM is equal to ton of refrigeration. TR means ton of refrigeration into 24 divided by delta T. So this delta T, for example, if you see the FCU, we have the fan coil unit, and this is supply line which is going with 45 degree Fahrenheit, which is going inside the FCU, and which is coming with 55 degree Fahrenheit. So the delta T, the temperature difference between the incoming and outgoing, is 10 degree Fahrenheit. But like you see in the many videos, this 10 degree Fahrenheit is not fixed. It is disturbed by lots of factors. So I will explain you one thing here, because I'll prepare a separate video how this delta T is determined, because there are different factors like variable primary system, variable secondary. There are different concepts will come when you talk about the delta T, and if the delta T is very low, what are the problem will come. So these are the thing I will cover in one separate video. So like first of all, I will understand what is the concept here. So for in our project, if you see here, so this is the overall view of our project, and this is the line which is coming from outside. If you see here, from district cooling, so there is a separate district cooling plant is located in somewhere, we have the district cooling plant, there the cooling tower and everything is located. From here the pipeline is coming, and here from this point we have the tapping to our incoming line, so which is going to the heat exchanger. So in this project we don't have the air cooled chiller, we don't have the water cooled chiller, and instead of those chillers we are using the heat exchanger. So it is called as a district cooling system. So if you go to different countries, for example if you go to Qatar, and they have some authorities like Qatar Cool and Marafa. Marafa is located in the particular location of the Qatar, and Qatar Cool is located in different locations. And similarly if you go to UAE, you can see the Emikool, Tabrid and etc. Different authorities are there. For example, if you go to Qatar, the district cooling primary side. So primary side means, if you go to this drawing, if you see here, there's a primary and secondary. Primary means this, if you see this line, so before this line, that means this heat exchanger left side. So the line is coming from outside. Now this line is coming from outside, which is going to the heat exchanger, and which is again going back to the heat exchanger. So this line is, this side is called as a primary, and this side is called as a secondary. So if you go to this concept, the primary supply line normally 5 degrees Celsius or 41 degree Fahrenheit, and the return line is 14 degrees Celsius or 57.2 degree Fahrenheit if you follow the Qatar arrangement. And distributed secondary side, it will be 6.2 and 15.2. So if you see the delta F, that means the degrees Fahrenheit, 43.16 and 59.36. So if you subtract both this answer, 59.36 minus 43.16, you will get the delta T of 16.2, 16. So similarly if you go to this UAE, for example the Emikool, the district cooling primary side 4.4, 13.3. So earlier how much it is in the Qatar? 5 and 14 degrees Celsius. But if you see the delta T, it is same for both, only the temperature is different. Here 4.4, 13.3 in the district cooling primary side. District cooling secondary side, that means the building side, it is 5.5, 14.4. It was in Qatar 6.2, 15.2. So that is the only difference. But if you see the delta T, 57.92 minus 41.9, it is still 16 degrees. So delta T is 16 degree for district cooling system. This is not for the air cooled or water cooled. Now our project is based on the district cooling system. So I'm showing the example for the district cooling in the UAE and Qatar. So in the district cooling system, finally the supply temperature, return temperature on the primary, secondary side, and if you see the Qatar, it will vary. But the concept is the delta degree Fahrenheit is 16 degree. That is fixed one. So let me explain this district cooling concept first. Then I will come to the air cooled or water cooled chiller concept. So in this formula, GPM is equal to ton of refrigeration. For example, if you have 1 ton FCU in your room. So if you apply this 1 ton, 1 into, first try with 1 ton, 1 into 24 divided by delta T. If the delta T is like a district cooling system, then as I told you, it will be 16 degree Fahrenheit. So if you try with 1 ton, 1 into 24 divided by delta T. For example, it's a district cooling system means 16. So it will be 1.5 GPM. So 1 ton is equal to 1.5 GPM. You have to follow for the district cooling system. So similarly, if you go to air cooled chiller, water cooled chiller, for example, the supply 7.2 degrees Celsius is 45, and return 12.7 is 55 degrees Celsius. The delta T will be 10 degree Fahrenheit. So similarly, you can say different delta T, like 7 degrees Celsius for 12 degrees Celsius. The delta T will be 9. And if you go to this data center chiller, it can be supply will be 15, return will be 20 degrees Celsius. So that there are different delta T will come based on the application. And now we are discussing about the chilled water pipe sizing. So we don't need to go that much very deep about the delta T. We will simply follow whatever is there in the schedule. So when it comes to another video, I will clearly explain how this delta T is determined. And for example, if you see here, and the delta T temperature, entering temperature 5.5, leaving temperature 14.4. So here this is for the chilled water, it is given, and in this example we will follow that. And for example here, if you go to this one, say like 1 ton, 1 ton if you have, so 1 ton means 1 into 24 divided by delta T. So in this application, delta T is 10 degree Fahrenheit. So if you follow this one, 1 ton, 1 into 24 divided by 10 degree. So 1 ton is equal to 2.4 GPM. If you have the delta T like a 10 degree Fahrenheit. So whatever the project is given to you for the chilled water pipe sizing, you have to verify what is the entering temperature and what is the leaving temperature for the equipment. So based on that, you can size the pipes. So in our example, the complete project is 5.5 into 14.4 only because of the district cooling system. So if you follow this concept like 5.5, 14.4, the delta T is 16 degree Fahrenheit only. So if you say 16 degree, what will be the answer here? Ton of refrigeration, for example, 1 ton into 24 divided by 16. So 1 ton you have to apply 1.5 GPM. For example, we will see what is the pipe sizing for this FCU RF02. So let's start with this one. First, we'll go to the schedule. So if you go to the schedule, we have to see the what is the total capacity. So here the total capacity is given in kilowatt. So if you know this tag number, if you see the tag number here, FCU RF02. For this tag number, now we will go to the schedule. So if you go here FCU RF02, we need to know what is the total cooling capacity. It is 3.3 kilowatt. So 110 is equal to 3.517 kilowatt is a constant value. So it will be 3.3 divided by 3.517. It is 0.938 ton. So you can, as I mentioned, 0.9 ton, and in our application now 1 ton is equal to 1.5 GPM. So I explained already in the before that. So I am multiplying with 1.5. So you will get 1.35 GPM for the FCU RF02. So 1.35 GPM means I am going to apply the velocity plus friction method. So first I will go to this pipe sizer. I will try with any size. For example, let's try with 2 inch. So 1.35 GPM. If you see the velocity is very low, 0.13, so we can reduce the pipe size. So I will go with the 3/4. That is the minimum pipe size we follow this one for the chilled water system, and the flow is 1.35. If you see the fluid velocity, it's 0.81 feet per second. So we can go maximum velocity of 4 feet per second. So I can go with the minimum pipe size 3/4 inch for this 1.35 GPM. So let's try with another one. You go with the next one. If you see here, which is FCU RF03. Now let's see the pipe sizing for this one. FCU RF03, which is here, and the total cooling capacity is 14.85 kilowatt. So 14.85 divided by the constant value 3.517, it is 4.22. So as I explained here, 4.2 ton, and I will multiply with the same delta T. That is the answer for the delta T is 1.5 we got now. 1 ton is equal to 1.5. So 4.2 means 4.2 to 1.5, it is 6.3 GPM. Now go to the pipe sizer. Just try with any size. First 2 inch, then we'll see 6.3 GPM. The velocity is very low, 0.6. So I can reduce the pipe size. Let me try with 1 inch. It is 6.3. If you see the velocity 2.34. So let me try with the lower size again. 3/4 inch. So 6.3. Now it's okay. So again velocity is 3.79 feet per second. So we can go with 3/4 inch here. So here also 3/4 inch. 3/4 inch, and above also I'll follow the same one. So this is the pipe size, and FCU. Okay, let's go to the example again. So these two we already finished. FCU RF2, FCU RF3 finished. FCU RF01. If you go to the schedule, FCU RF01, it is 3.3 kilowatt. It's same kilowatt. So 3.3 means the pipe size will be same. Well, we can follow the 3/4 inch. The same one we can follow here. And the next one. Okay, now you decided these two pipe sizes. This one, and this one we know. So what about this combined pipe size here? So we need to add these 3 flow. Then we get the answer. For example, here we have to add 3 flow. That is 1.35 GPM. Means this flow plus this flow plus this flow. These 3 we need to add here. So 1.35 plus 6.3 plus again 1.35. The total it is 9 GPM. So if you go to the sizer, let me try with the 1 inch first, 9 GPM. Okay, so still the velocity is okay, 3.34. Let me try with again the old size, 3/4 inch, and the flow is 9 GPM. You see the velocity is exceeding 4 feet per second. So it is not acceptable. So I need to go with the next higher size, 1 inch, and 9 GPM. It is 3.34 feet per second. So if you go to the drawing, so the size at this point is 1 inch. Pipe size, and we decided the pipe size for these 3 individual pipe size. Now let's see, we have one AHU here. Let's see what is the pipe size at this point. So the AHU number is AHU7FL. If you go to the chart, means the schedule, we can see here AHU 7FL we have to follow, and we have to see what is the total cooling capacity as I told you. So here the total cooling capacity is 85.6 kilowatt. So 85.6 means what is the ton? 85.6 divided by the constant value 3.517 to convert to the ton. So it is 24.3 ton. So if you go here 24.3 ton, and I have to multiply with the fixed value 1.5 for this district cooling system. So it is 36.45 GPM. Let's go to the pipe sizer. First try with the 2 inch or 1.5 inch. It is 36.45 GPM. The velocity is 5.74 feet per second, which is not acceptable. And we have to go with the 2 inch. Then try with the 36.45. The velocity is 3.649. So it is acceptable. We can go till 4 feet per second. So finally, the pipe size for this AHU, I mean this AHU, it will be 2 inch. So we can go with the 2 inch for this one, and here it will be 1 inch and 1 inch. Here it is 1 inch. On all these three is 3/4 inch. And if you go to this area, then you have to add this flow and this 3 flow and this flow. So total, if you add all, you will get the answer here. So here again FCU RF03 is given. So we already know the FCU RF3 value. Let's try this one. Okay, so FCU RF3, I think, okay, we need to do it again. So if you see here FCU RF1 and 2, which has same capacity 3.3, 3.3. So only the RF3 is 14.85 kilowatt. So here it is not RF2, this is RF3. So now you will get the answer. Like for example, RF2 it is 1.35 GPM, RF3 it is 6.3 GPM. Let's go to the diagram. We have RF2. So RF2 means 1.35 GPM. So let's add all the value. First 1.3 GPM, and we have one RF3 here. So for the RF3 it is 6.3 GPM. So I will add this one 6.3 here plus 6.3 GPM, and again we have RF1. So again I will add 1.3 GPM, and we have one AHU. Again we have one RF3 here. So this RF3, you know the answer here. For the RF3 is 6.3 GPM. So I will just add that one plus 6.3, and finally we have one AHU here. So the AHU value, you know that 36.45. So that one I will again add here 36.45. So finally 51.65 GPM at this point. 51.65 GPM you have to follow. So if you know this GPM, you can find out the pipe size. So here, and here you can try with the 2 inch first. So we need 51.65. You see the velocity which is more than 4.94. So as I told you earlier, if the velocity is more than 4.4 feet per second, then you have to go with the next method. Next one is called as a head loss. You have to follow the head loss because you are following here velocity plus friction method. So here the velocity is exceeding 4.94. Now we have to see the head loss only. The head loss here how much? It's 5 feet per 100 feet. So which is not acceptable. We have to make sure the head loss is less than 4 feet. So that means what we have to do, we have to increase the pipe size. If you go 2.5 inch, you can follow 51.65. Now you see what is the head loss here, 2.101. So this is the acceptable pipe size. So if you go to this point, so if you go to this one, the pipe size, okay, so at this point the pipe size is 2.5 inch. So we know what is the pipe size here, here, and at this 3 point, at here also. So like this, one by one you have to add all the pipe size by getting the total kilowatt from the schedule, and you convert to the ton of refrigeration, and one by one you can add all the pipe size. You can come back. So finally you will get one by answer here, 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 and finally the riser also same concept, because if you know the all the flow at this point, for example, let's say consider 100 GPM here, and the 100 GPM size will come for the riser also, because here we are not following the velocity method. I am following velocity plus friction method. So the location of whether it is a riser or the tapping point or soft point or header is not an issue. You can follow the head loss and the velocity value only. So now it will go like this, header one by one by adding the flow. Finally you can go to the ETS room. So you can get the pipe size for the ETS room also by adding all the combined flow one by one. So this is the way to size the pipe sizer for the complete project, whether it is a low rise, medium rise, or high rise building. This is the concept we have to follow. So I would recommend you to follow this velocity plus friction method as per this ASHRAE application handbook. We can follow this method. So I hope this concept is clear. Still, if you have any doubt, please add your comment in the comment section. Thank you. Bye bye.